Hello, we are Group 9 and we will talk about row transfer machine design. This project requires us to design a mechanical system to transfer paper rolls. To do it, we must consider the mass and the size of the paper rolls, and the cradle and the material and the thickness of the support table. And we must analyze each component, including lead screw, gears, bearings, and bolts. Other analysis of cradle and support table and the external effects are negligible. Friction is negligible if not specified.
This slide shows our full CAD mode. It includes all the main structural and moving parts. The only part not shown is a motor, which will be installed at the end of the lead screw. This CAD mode reflects our earlier product choices. Some parts in the final design may look different, but the layout and the function are the same. The motor turns the power screw. This makes the nut move sideways. The crank arm is connected to the nut and changes this motion into rotation, turning the gear. For the bearing, we use two pillow block bearings to hold the shaft. They are spaced 800 millimeter apart to reduce friction and keep shaft straight. For the bolts, each bearing is fixed to the base using two bolts. This helps keep everything stable when torque is applied.
We first calculate the weight of the paper roll with the supporting arm and calculate the torque for the initial case, which is maximum torque. Based on the number of teeth of the gears, we calculate the torque required for gear 2 and the tangential force between them. From the free body diagram, it's clear that gear 1 also gives the force to the shaft, which is critical for our bearing analysis. Finally, we use the Lewis equation for each gear and calculate their bending stress, which gave us the factor of safety for gears, making sure they are all above 2.
This slide shows the free body diagram of the gear and crank arm. We assume the dashed line splits the angle phi2 into two equal parts. The nut moves at a constant speed and travels a distance d in 45 seconds. We also assume the friction coefficient is 0.15 and the crank arm is 250 millimeter long. To find the motor power, we calculate the angular speed of the screw using the lead and the time. The power is calculated using the torque and speed. We set the factor of safety to 2.0. We also assume the efficiency from the motor to screw is 90%. The final required motor power is about 533 watts. This is a free body diagram for the screw. We use the screw dimensions and friction to find the torque required to lift the load. The torque we get is about 25.16 Newton meter. Here we check the safety of the screw. We use applied torque and the minor diameter to calculate the shear stress. The material is 1018 carbon steel with an allowable shear stress of 255 megapascal. The result gives a factor of safety of 2.17, which is greater than 2, so it's safe. To check self-locking, we use this condition. The lead must be smaller than mu pi dm. We plug in all the values. Since 6.35 millimeter is smaller than 2244 millimeter, the screw is self-locking. This page shows the force analysis of our bearing. First, the shaft, arms, and rolls apply the total downward force of 9.43 kilonewtons. Second, the gear applies another vertical force of 19.47 kilonewtons. We use force balance and moment balance to find the support forces. As a result, for the bearing one, it supports and 34.22 kilonewton downward. For bearing 2, it supports 24.18 kilonewtons upward. This tells us how the load is shared between the two bearings. Here we calculate the bearing lifetime and factor of safety. The basic dynamic load rating C10 is 104 kilonewtons. Using the formula, we find the life in revolutions is about 28 million. This gives us a lifetime of 1.4 million hours. So our bearing is 7 times stronger than needed for 99% reliability. Also, the factor of safety is greater than 3.15, which is very safe.
Bolts are used to tighten the iron bearing support frame and the steel support table. Bolts can be fatigued under the total load of preload shelves and the load of the paper roll and the cradle. We use the M10 class 8.8 steel bolts to do calculations. Its total length is 45 millimeter. The preload is around 33.7 kilonewton, and I determined the external load based on the mass of the paper roll and the cradle, and the gear force applied to the shaft. After calculation, the constant C is 0.139. The factor of safety against the separation is 2.01. The load factor is 2.55, and the fatigue factor is 2.03. The bolt on the right can satisfy the requirement and each costs $5.75.
So for our design, we focus on keeping things both efficient and affordable. We use a relative large gear ratio, which helps reduce the torque needed on the second gear, making motor power lower. The lead screw we choose has a large pitch and is self-locking, so it saves power and keeps the system safe if the motor stops. All of our parts are standard off-shelf components, no custom machine needed. And for every part, we pick the cheapest option that still meets all the requirements. So we cut costs without cutting safety. Even though our design is solid, we also look at where things might be go wrong. For gears, we consider the teeth fatigue from high force. So we use large module and wider face. Our safety factor is over 2.6. The lead screw is self-locking, so even if power cuts out, the system stays safely in place. And it has a safety factor of 2.17, so we are covered there. At the same time, we have select bearing with a lifespan of 7 times the required to prevent unnecessary damage. And for the bolts, we make sure to apply preload and check that the factor of safety is above 2, so they will hold up long term. Here is our bill of materials. We list their vendor as well as their part number. Since the price of the two gears needed to be quoted, we have not counted them for now. The rest of the total price is 714 US dollars. Thank you for your listening.